Okay, now we're going to turn to looking at the projection operation and look at the functions that we're going to provide in MVJS. There's going to be two of them. Well, actually three, one for orthogonal viewing and two for perspective viewing. And we'll have to look a little bit at the mathematics here, and we'll look more at it next week when we get the full projection matrices. But what I want to do is at least introduce it at the point to understand that we're going beyond the affine transformations we've been using before to get rotation, translation, and scaling, which we could have used to position the camera. But now when we start talking in particular about perspective projections, it gets a little bit more complex, and we go into what are called projective transformations. So let's start with the simplest possible projection, which is we do an orthogonal projection, and we project directly into the plane z equals 0. That's what we've been doing essentially by default, because if we don't do anything else, the clipping and clip coordinates assumes you have a orthographic projection. What we're going to see next time is that the way we get a more general case, because I went through this lecture with classical viewing, and we said, oh, what happens if you now move the projection plane and it's no longer parallel to a principal face, and what happens if the projectors are not orthogonal to that projection plane anymore? Well, it turns out we can get all of those, but the trick will be that in order to implement this and use the hardware, where the hardware is really geared towards doing orthographic projections. In fact, it's exactly what happens in clip coordinates. What we're going to do is go through a process called view normalization, where we convert every other view to this default view. And so the idea is that we distort everything so that the projection of the distorted image gives us the projection we wanted in the first place. And that's what we're going to be talking about next week. So today, don't worry too much about, oh no, that isn't the most general view, because if you can do the simple view, I'll show you next time how you can do the more complex views. So here's the simplest projection, and if I want to represent that in homogeneous coordinates, we use this simple 4x4 matrix. It's almost an identity matrix. It leaves the x alone, it leaves the y alone, and converts the z to 0 and leaves the w component alone. So that if you project a point, you get x, leave y, set z to 0, and leave the w component alone, so you know that it's a representation of a point. Now, however, there's one little bitty change we're going to make. We're going to say the default here really is going to be an identity matrix, so we'll put the 1 back. And that has a couple of important effects. One is we now have an invertible transformation. We can always set the z equal to 0 later. The reason we don't want to do it up front is that, besides this lack of invertibility, is that we need the z information later when we do hidden surface removal. As we'll see more in a little bit later, is that hidden surface removal is really not done until after you go through the fragment shader. So we need depth information so we can make that decision later in the pipeline, and we can't do that if we wipe it out here. So the projection matrices will have that one, the default one. Another way of saying it is that this matrix is non-singular. It has an inverse, it has a determinant which is not equal to 0. But the important point here is we're preserving depth information. We may alter the scale, we may do things like that, but the order in which points are in depth will not be changed, even though their positions might be changed in z. Okay, so let's look, that's an orthographic or orthogonal projection. What about perspective? Well, let's take a simple one, and there's a couple of different ways to get the simple one, because the problem with perspective is that we can't have the projection plane in the same plane as the center of projection, or the equations blow up. So what we're going to do is put the projection plane out now in front of the center of projection, down in the negative z area. Other books will do it by putting the projection plane at z equals 0 and then moving the center of projection back along the z-axis. I prefer to do it this way because the equations come out a little simpler, but it's not a major difference. So here's, if I look at that from the top view and the side view, I get two pictures that look like this. So I'm taking this and I'm looking at it from one side, and I'm also looking at it from the top so that I can get equations to give me where does x, y, z project into. Okay, now I know the zp is always going to be wherever I place this plane, but what are xp and yp? And I get that basically by looking at the side view and noticing that the triangle I form here is the same as the triangle I form by just dropping a perpendicular from x, y, z, and then I can use the fact that the ratios or the tangents of those angles will be the same. So here's what you get from a top view. We're looking at it from the top. So remember, the z is going down when I look at it from the top. The x is going to the right. And I have these two similar triangles, so therefore these ratios of x, p to x is the same as the ratio of d to z. Okay, well, here the assumption is that d will turn out to be negative here because I pushed it into the negative, but that's okay. If this is -1, then this becomes just minus x over z. Likewise, when I look at it from the side, I see the yz plane. So now I have z equals d coming up straight up here. Again, these two triangles are similar, so I get the equation yp equals y over z over d, which are the standard form of perspective, and the z's are always the same. I mean, I'm always projecting into this plane zp equals d, so these are the three equations. Now, this doesn't look like homogeneous form. As we've seen way at the back at the beginning of the class, this explains a lot of things about perspective, because if z is larger, meaning that the object is further from the viewer, things get smaller because the projection gets smaller because you're dividing by the value of z. You also see that these equations for x and y, the projections, are nonlinear. So you think, oh, this is a different world. Everything we've done so far is linear. But here again, homogeneous coordinates come to your rescue. If I look at this in homogeneous coordinates with a certain 4x4 matrix to represent this projection, look at what happens. So here's the matrix I want to use. Notice what it'll do. So I'm going to multiply it by x, y, z, 1. So it leaves the x alone, x times 1, y times 0, z times 0, w, which is 1 times 0. It leaves the y alone. It leaves the z alone, but it does something different to w. Remember, long ago I said in homogeneous coordinates, if it's a vector, the w is 0. If it's a point, the w is 1. But the generalization of that is as long as w is not 0, it's going to be a point. But we prefer to have w equals 0 because then I don't have to worry about dividing it out. Here, I'm actually in perspective going to change that w, because look at what this equation says. It says multiply by x, y, z, 1 on the right. 0, x times 0, 0, y times 0, 0. This term is now z over d. And the w 1 multiplies 0. So this is what you get out. If you do p equals m times q, you get x, y, z, z over d. That doesn't look familiar unless we do one trick. In homogeneous coordinates, the rule is that in order to go from 4 dimensions back to 3 dimensions, you divide by the w if it's not 0. So if I divide by this w, look what happens. X becomes x over z over d. That was the equation we just had over here. If I divide by the y term by z over d, I get the y that I had over here. And finally, if I divide the z by z over d, the z's cancel out. I get 1 over d, which is in fact just d, which is the value of the projected z. So in fact, if I use this particular matrix, I do get the equations of perspective. So this is our basic perspective transformation, which required this one extra operation because I didn't maintain W as 1, which is known as perspective division. So here's, this is just saying that we have to do this perspective division. Do we really care? No, because it says, oh, division is going to take more work. That was true in the very early graphic systems. It was a really big deal when the first Evans and Sutherland system came out, and it actually could do perspective when any of the other systems at that time couldn't, because it actually built a division into hardware. Now it's basically just a non-issue. So perspective requires this. This is known as obviously as a perspective projection, and this is a perspective projection matrix. We can use it in a way, as we did with the orthogonal, make it non-singular. We'll put a constant over here so it's non-singular, and so that we can maintain depths. And next lecture I'll show you how we change these two terms here so that we can do that and maintain that information. But for now, this is the important thing, that it's another wonderful extension of our use of homogeneous coordinates. Okay, now let's look at the actual functions we're going to use in WebGL. So here's orthogonal viewing, whether it's WebGL or desktop OpenGL. The old function was called ortho, and what you start with is you start with a clipping plane. So this is how we describe our synthetic camera lens, not necessarily by the angle of view or by the focal length as you would with a standard camera lens, but by describing the volume that it sees. So in orthogonal, all the projectors are parallel, so what I wanted to do is describe a box here, and I could describe it in any plane, but I could do any plane of constant z by giving you the bottom left corner, which has an x coordinate of left and a y coordinate of bottom, and the top right then has coordinates right, top, and if I allow now, which I will, front and back clipping plane, then you have a minimum z and a maximum z. Now here's one place where it could be a little confusing, but as long as we're consistent, we shouldn't have a problem, is that historically there's always been this problem of left versus right-handed coordinate systems. That art people tended to use a left-handed coordinate system, all the engineering people and now virtually all the graphics people prefer to use a right-handed coordinate system. Now you can use your right hand to say, oh, if X is your thumb and your index finger points up, that's Y, and it's right-handed, the Z points out of the plane or towards you if you're using your hand. Left-handed coordinate system, if you have X and Y this way, Z points the other way. The problem is that if you don't know which, you're obviously pointed in the wrong direction. There's a tendency, and older graphic systems did this, and I remember it was very, very confusing. When they did the modeling, they were in a right-handed coordinate system, because that's what engineers and mathematicians and scientists like. When they did the viewing, which was considered more sort of the artist's view, they switched over to a left-handed coordinate system, which would have been okay as long as you had no access to anything past the front end. But if you had any functions that manipulated what went on side, in particular functions that affected the viewing, now you had to worry about, oh, these parameters in a left-handed system, these are in a right-handed system. So OpenGL in a way is sort of in the middle. And in fact, in OpenGL you do have the desktop, you do have the ability to say, I always want to work in a left-handed system. But let's start the way we're going to do it in most people. We're in a right-handed system. The only place you're getting into a problem is right here. That the distances of the camera, so here's this default camera sitting over here at the origin, pointed in the negative z direction. And it has a front clipping plane saying everything before that front clipping plane we're not going to see, and it has a far clipping plane, which everything past there we're going to throw away and clip out. And that's why we get this box. But the distances for near and far, the distances in this function ortho, are going to be measured from the camera. They're not going to be z values. See, left, right, top, and bottom are values in the XYZ space. Near and far are distances from the origin to the front clipping plane. So I want, in this picture, I want a positive value here because that'll give me a negative value of z because this box is in the negative z plane. So I have to, so as long as you remember that distances in the ortho and then in the other functions we'll see in a minute for near and far are distances from the camera. The far distance should always be greater than the near distance. You'll be fine. And think of left, right, bottom, top, and near as just being the corners of that rectangle that you're looking at in X, Y, Z space. Okay, so perspective is essentially the same, except you're getting something called a frustum. It's a pyramid and it's truncated. Okay, so that you have a near plane, a far plane, and again you have left, right, top, bottom, near. Now the only little trick here is that because the distance, because this is a pyramid, the size here is different than the size of the front plane is different than the size of the back plane. So the rule here is that left, right, bottom, and top are in the near plane, not in the far plane. Okay, so as long as you remember that, you'll be okay. Now another thing to notice, let me come back to this view. This view is actually enough to encompass a much broader kind of viewing, because you can say, well, what if I, it doesn't have to, let's put it this way, it doesn't have to be symmetric with respect to the XYZ system. So I don't have to have that left and right are negatives of each other, and bottom and top are negatives of each other. This could be a skew symmetric box, and that has implications for what you're going to see in terms of getting isometric, axionometric kinds of views. In this case, you can get this will determine how you get 1, 2, and 3 point perspectives. If you think about aiming this triangle in some arbitrary direction, you sort of can get a feel of what this is going to do for a viewer that's looking at it. So this is a pretty general formulation. The problem with this formulation for perspective is that often if you don't have a camera pointed just right and these parameters picked in some reasonable way, you might not see anything in your scene. And so there's a second interface to perspective views that was in the original OpenGL. We put the equivalent function into mv.js, which is called a perspective view as opposed to frustum. Frustum is going to be more general, but often people prefer to get started with perspective. So here this maybe is closer to the interface you'd have with a camera, where you provide the field of view, okay, which is an angle, or sometimes called the angle of view, but more likely the field of view. And that says, how much am I going to see? Is it a wide angle lens where I see a narrow angle, or is it a fisheye lens where I see a very wide angle? And so what you can do very easily if you use perspective is that you can take the field of view to be very large, and as long as you're pointing in the right direction, you'll capture things, but you maybe capture too much but then you could adjust that fairly easily and then maybe switch to frustum after. So this is a very handy one. It's less general for couplers. First, that you specify again the near and far distance, and you specify the aspect ratio, the width to height ratio of the front and back clipping planes. So it's only got 4 parameters to specify. The field of view is going to be different. It's FOVY, it's called, because it's the angle when you look in the y direction as opposed to the angle if you look down from the top. And so if the aspect ratio is other than 1, those 2 angles will be different. But the main problem here, or the main lack of generality here, is this is always going to give you a symmetric view. It's always going to give you a frustum which is symmetric about the z-axis and symmetric about the y-axis. You don't have to have it symmetric here in a general frustum view. You can have this pointing all the way off to the left. So for example, left and right can both be positive. Bottom and top can both be negative depending on where you point it. Here, the assumption is you want a simpler symmetric view, or in terms of this pyramid over here, it's a right pyramid. That if you take the normal in the center, it goes right along the axis. Okay, now let me finish this up by looking a little bit at computing some of these matrices and using them in an application. And this is from a program that's under chapter 5 called Perspective 2, and there's a program in there, ortho, and a program that let you use slide bars to manipulate a bunch of these parameters. And this is trying to illustrate a couple things. It lets you fool around with the views, but I think it also shows that the interface could be done. This is a much more natural interface. Here I'm adjusting the field of view. Here I'm adjusting the aspect ratio so I can make this cube into more of a parallelepiped. I can rotate the cube by theta and phi to two directions. And radius here is a measure of where I'm putting the camera, and it's a certain radius out from the center of the object, and where the near and far planes are. Okay, so let's look at that for a minute. Let me see. I think I have it on the screen. Let me see if I can shift over to it. Okay, so here it is over here, and I can fool with it. So here it is. I think you can see that that's a perspective view. I didn't make it particularly dramatic here, so I could distort it, but this is just distorting the size of the cube. This is just changing the aspect ratio. I can change the field of view, which does have the effect of changing the perspective a bit. And I can rotate the thing if I want. See, rotation gets a little stranger because you can't do everything about the origin in perspective, but you see. Now, the thing I wanted to demonstrate here is you have to be careful about the near and far clipping planes, because those clipping planes are measured from the camera. So if I start moving the camera, I'm moving the clipping planes. The clipping planes they're in camera space, they're not in the world or object space. So you can very easily, by moving the camera, start clipping your object, and I could show you that. I guess I can do that here, sort of what happens. Let's see, let me grab this. If I can really. I want to change the near plane. That's what I want. See, now what I'm effectively doing, well, I'm just moving the near plane in this. And notice now you're seeing the inside of the box, and you're seeing the colors of the other faces. So you have to be very careful of that. Or if you do something like, if I try and rotate it, let's see, rotate it. You see what I'm clipping or not clipping changes when I do that, and that's going to be true in an orthogonal view too. So let me go back to the slides and try these. Try these. There's the ortho. There's two perspectives in there on the website. So going back here, let me come back to this picture. Let's do this one. You see, these are attached to the camera, and these planes, and so here's your clipping volume. And if I start playing around with this clipping volume, and the object is staying where it is, but I'm moving around the volume, I'm going to wind up potentially clipping out different things. And if I make the volume too big, then in perspective, I may make the objects too small, or I may see things I don't want to see. So there's this interaction you have to be a little careful of. Okay, so let me finish up by looking at how we actually wind up using. So here's a part of the JavaScript code from Perspective 2, and I just want to show you that we're using, so this has both parts in it. Okay, it has a model view matrix, which is going to be computed just using the lookat function. All I want for that is, see, I'm still rigging the coordinates, so I don't have to scale the objects yet. But I just want to get the view I want. So lookat here is changing where the viewer is. In this application, I think I have the viewer just circling around the object and always looking at the center, and the up direction is always the y. So somewhere outside of here, there's global variables that set the at and the up. But as I go along, what I'm doing is I'm changing the position of the eye, and here's just some trigonometry. To do that, and within the render loop, I form a new model view matrix. I form a projection matrix, using the perspective function, using near and far. All of these have been set globally. I'm not changing the projection. But one of the big points I want to make here is where are we actually doing it? We're doing it in the vertex shader. So I now use the GL uniform matrix for FV function to send out the model view and the projection matrices, which are set up as we did when we were talking about transformations and moving them to the shaders. And we need the flatten function to convert them into 16 constants or floating point numbers that are used by OpenGL. And so we send out the model view matrix, we send out the projection matrix, and I draw the arrays and I sit there in this render loop. The shader itself in this kind of example is almost trivial. It takes in a position. If we're doing our standard thing of interpolating colors, we send in a color and then I just send it on as a varying variable off to the fragment shader, the rasterizer, which first that will convert it into a color for each fragment by interpolation. That's what we were doing before, and now I bring in these two matrices as uniform mat 4s from the application, and now look at what I have to change. All I have to really do here is multiply the position by first the model view matrix and second by the projection matrix, and now that's my output position. So it's very, very simple once you sort of know what you want to look at and what you want that volume to be, and whether you want a perspective or orthogonal projection. It's very, very simple to carry all of this out within the shaders. And if you want to change the shaders in time, change these matrices inside the shaders, sure. You can send a time variable over here and then do the trigonometric calculation through the functions in the shader. So it's all pretty straightforward to do. Next lectures, we'll start looking at what the underlying mathematics of this is.